All right. So, this is week 5 now, and today we shall be discussing about syntax in natural language processing. So, mainly in today's talk, we are gonna mainly discuss about these grammars and interconversion of different grammars and so on. Because, as you know, this week's material is mostly based on context-free grammars and so on. So, because these are slightly difficult concepts, so we'll go through them slowly so that we can understand the different ways of understanding these grammars and converting between them, so on. So, let us begin. So, for example, this is the first question. So, this is based on context free grammar CFG, and you have a CFG given in the form below, which is the starting symbol S gives A or CB or C. B gives CAA or epsilon, which is empty, and A gives BC or B. So the question is about how many non-terminals, actually not terminals, how many non-terminals should be added to convert the CFG to CNF. So that is like the second part of the question. You can think the main part or the learning part is about converting the CFG to Chomsky normal form or CNF. So, as you know, CNF form means that first of all, because this is a context-free grammar, you will be only having a single non-terminal on the left-hand side. So that is already known. But to convert to CNF, the right-hand side can be only one of two forms. That is, either it can be a single non-terminal. For example, S gives C is a valid rule in CNF, or it can, or if there is sorry, it can be a single terminal, which is S gives C, or if there are non-terminals, there must be exactly two of them, and there should not be any combination with other terminal symbols or anything else. So either rules of the form X gives YZ or X gives A. These are the only two type of rules which are allowed in Chomsky normal form. So we shall look at how we can convert a CFG to CNF using some heuristics. So firstly, as you know, in a CNF, null productions are not allowed. So these are null productions, like B gives null. So in CNF, null productions are not allowed. So we need to remove the null productions. So how do we do that? Like there are some rules before that also, like if the start symbol occurs in the RHS, we got to deal with that and so on. But we don't have that over here. So the first thing we need to take care of is the null production. So the simplest way of replacing the null production is that you see B gives null. So we look into the rules where B occurs on the RHS, and over there we replace the B with the rules from the this one, the second rule. So then what we can get is that we will effectively remove this B gives epsilon part. Then, so if you look, we have S gives A or CB or C. Okay, so there's a B over here. Now this B can give C double A or epsilon. Now we want to remove the rule B gives epsilon. So then we have to consider what happens if B does yield epsilon under this rule. So then that becomes S gives C if B does give epsilon, right? So we don't need to make any change over here because C already is there. So that is why S gives A or CB or C. We make B gives CAA, we remove the epsilon part. And if you look over here, if we replace B with epsilon, we get only C. So a new rule gets added over here, which is A gives BC or C or B. And then B can give CAA. And you have removed successfully that B gives null part. So that is the first step, right? So far we have not had to introduce any non-terminals due to this step. Now we need to, as I said, in CNF we cannot have on the RHS non-terminals and terminals occurring together. So we need to replace all such rules where the terminals are replaced by a non-terminal, and then we give a simple rule that the non-terminal gives that corresponding terminal. So what do I mean by all this? For example, take a look at here. Here you have the rule S gives CB, and here you have the rule A gives BC, and here you have B gives CAA. Now here in these three rules, the terminals and non-terminals are occurring together. So say we can make a rule like this: X gives C, and in these rules we replace wherever we have C with X. So S gives XB, and B gives XAA, and A gives BX. So we can easily do that, and we have done that by giving this rule, which is X gives C. So we are introducing a new non-terminal over here. All right. So now, as you can see, the grammar is shaping up. We have removed null productions and we have removed combinations of non-terminals and terminals. Now what is left? The only part that is left is we now need to remove all those situations where on the RHS we have less than one, or sorry, less than two non-terminals or more than two non-terminals. So we need exactly two non-terminals on the RHS of every rule. So what are our biggest problems over here? So one is this rule B gives XAA, because there are three non-terminals on the RHS. And the second one is this one, S gives A. There is only a single non-terminal on RHS. So we need to take care of these two situations. So how we do that is, over here you can directly replace the A from this rule. So we know A, the only thing which originates from A is A gives BX or C or B. So we can directly put this part over here. So that gives S gives BX or B or XB or C. So this becomes the entire rule now. And we have effectively replaced the X. Right. And for this part, we can take XA to be a new non-terminal, which is Y. And then Y gives XA. So here we are introducing a new non-terminal, and we are making sure that this rule also gets reduced to 2 on the RHS. So now if you have a look, all the rules right now, they are in the CNF form, because we either have a single terminal on the RHS or two non-terminals on the RHS for every rule. And that is the goal, right? So that is our final grammar. So we have S gives BX or B or XB or C. Okay, so I'll just reiterate over here. S gives BX or B or XB or C. B gives YA and Y gives XA. And on the other hand, A gives BX or C or B and X gives C. So this becomes our entire grammar in CNF. So you can see all the rules, they have either two non-terminals on the RHS or a single terminal. And so how many new non-terminals we have introduced? So we have introduced two new non-terminals. Okay. So that is this question. So this is relatively simple to start this off. After this we will have more complicated things. So if you have any doubt regarding this part so far, you can tell before we move on. Alright, I guess this is okay. So let's move on. So now this is a question on probabilistic CFG. So as you know, in a probabilistic CFG, a probability is assigned to every rule. Like what is the probability that given the symbol S, we give AB, that is 0.5, and we get BC is 0.5. So the only thing about PCFG is that starting from the same non-terminal, every possible rule, the probabilities have to sum up to 1. That is the only constraint. And apart from that, it's very similar to how you would treat with a normal CFG. So let's see. So now they're asking what is the probability of the string AAAB. Now if you know that under a CFG we can have many parse trees for the same string, because usually these grammars, they are not non-ambiguous. So there can be ambiguity, hence there can be more than one parse tree. So the probability of a given parse tree is we multiply all the probabilities in the chain, and the probability of any string is like the sum of all the parse trees which can be constructed for the given string. So we have to find out the different parse trees for a given string, and then we have to calculate the probability of each tree, and we add them up to get the probability of the string. So this is the overall procedure. Now let's see. So as you know, there are these methods for parsing strings, such as we have the CKY algorithm and all these things. But we shall start off with a more intuitive way before we get into questions like that. So because this is a simplistic grammar, you can actually find out all the possible parse trees without following any algorithm as such. So you just need to look out for what are the possible combinations you can apply. So how do we do this? Let's see the procedure for that. So let's consider, let's think of the ways we can construct this string a, right? So we are trying it out in a top down manner. So let's start with the first rule, which is S gives AB, right? Now we know one thing, you have to look at these rules, which is A gives A, B gives B, and C gives A. So if we need a terminal B at any position, we can only get it from this non-terminal capital B. And if we need a, we can get it from either A or C. Similarly, non-terminal C and non-terminal A can only yield the terminal A, and this non-terminal can only yield this terminal B. So this is the thing you have to keep in mind while creating the parse tree. So what do I mean by that? So let's have a look. So we have, let's take the first rule, S gives AB. Fine. Now we know that the string we want to get is A, B. So there's a B in the end, and this B can generate that B. All right. So let's keep that thing in mind, and let's look at the first part. So we can expand A. So as you know that we have a 4-length string, so we at least need a combination of 4 non-terminals. From there we can derive each single terminal. So that is our objective, that we first need to reach a combination of 4 non-terminals. Now we can expand this part, A gives BA. So you get this BAB. We could have also used some other rule combinations, so that those will be the other parse trees. So here we are taking one conscious choice after the other, and the other choices will be taken for the other trees. Okay. So S gives AB, and then from there you have BAB. All right. Now we know that from the non-terminal B we can either get this terminal B or we can get this CC. If we expand this B into the terminal B, we will have a problem because the string we want to derive is AAAB. So there should be A's in the beginning. So somehow we have to get this B to generate A's. How do we do that? Well, we know that C can generate A's, right? So since C can generate A, so we do B, from B we use this rule, B gives CC, right? So we get CCAB. And now we know that this combination can give us the string we desire. Because C can yield A can also yield A, and B will yield B. And what do we do over here? We keep on multiplying the probabilities of every rule we take into consideration. So the first one was this rule, and it had a probability of 0.5. Then we applied the rule A gives BA, that is 0.3. Then we applied B gives CC, which is 0.4. And then we apply the individual rules C to A to A, and B to B. So C to A is 0.8 square, and then this is 0.7 and 0.6. So this is the probability of the first tree. So this is how we get it, 0.016128. So it's a big number, but this is the probability. Just one second. All right. Now we need to look at the other possible combination of rules we could have taken. So as you know, over here we took the choice of converting A to BA, right? What if we did it the other way and did something like, so S gives AB, and then we apply the rule B gives CC. All right. So now we have ACC. So we are applying the other possible combination of rule, which is A B gives CC from here. Now we have ACC, and all these three non-terminals will only generate terminal A's. So we need something at the end which will generate a terminal B. So now we know that there is this rule C gives AB. We can apply that directly over here. All right. And as you can see, now we have that form of AAAB. And this is how we get the probabilities on the RHS. Now the interesting thing here is that starting with the rule S gives AB, we have exploited all the possible choices we could have done. Why am I saying that? Well, in the first case we took S gives AB and we expanded the A, and the only way to expand the A is this one, which is A gives BA. And once we have done A gives BA, we don't have any other choice except doing the rule B gives CC to get the string in this format. So because we have to get the string in this format, there are some constraints as to which rules we can apply and which we cannot. So because we have chosen this rule first, S gives AB, and then we have chosen A gives BA, so after that there are no more choices. This is the only option, and so we get this. So the other option was, instead of expanding A gives BA, we can expand B gives CC. So that is the second parse tree. And we have exhausted all the respective options for that also, because once you apply B gives CC, you get it in this format ACC. There is no other option but for you to apply this rule of C gives AB, and then the rest follows. So there is no other option over here. So we have exhausted all the options. So thus, starting with S gives AB, we have looked at all the possible combinations, how we can parse the string AAAB, right? So now the only other thing left for us to do is start with this rule S gives BC. So this tree has a probability of this. I guess this is straightforward. You just multiply the probabilities of the rules you apply, and the total product is the final probability of the given tree. Finally, this is for the third parse tree, and we take this option, which is S gives BC. Now, taking S gives BC, what are our options? So one option was that we could have taken this C and we could have given AB. So it would have been BAB. All right. But then we would have got stuck. And that is why we take this route. Because once you get BAB, after that, the ending B, you can either convert to CC, which means you can no longer reduce it to a non-terminal, or you can do B gives B, but then you would have a problem with the other part. So this is the only rule we can apply over here, which is B gives CC. And then we apply this rule, which is C gives AB, because we need a B at the end. We need A's in the beginning and a single B at the end. And finally, we get the string AAB, right? So this is our third parse tree. And as I said, there is no option to use the other rule over here, which is C gives AB, because then you would have BAB and then things would have got stuck, right? So after that, we get these three options. So the thing is that you can do B, like you can do C gives AB first and then B gives CC. So it does not matter in which order you apply the rules, but the parse tree is effectively the same, right? So that is why we have S gives AAB, and we have this probability. And so finally, the probability of the entire string AAAB is, you just have to sum up the three probabilities, and this is the final answer. So, okay, before we go to the next question, so if you have any doubts for this question, so once again, let me just go over the idea quickly. So the idea is that we start in a top down manner. We start with the string s, and we try to exploit all possible combinations that we can use. And so here we exhaustively use all the combinations. We first do s gives ab, and then we try all the possible parse trees with s gives ab. And after exhausting that, we try the other rule, which is s gives bc, and then recursively you can think we are exhausting all the other options also. So this is how we come to three parse trees in total. There are other methods to get this also. This is a very intuitive way. We are not following any algorithm or any structure per se. We are just looking at the string and the rules and trying to get this. So why is this useful? Because not every time it might make sense to apply big algorithms like CKY and all that, where you can just derive things by having a look at the rules. Then again, this might not be possible always, but because you have these nice setups over here that only this non-terminal will generate only a, this will only generate b, this will only generate a, so that's why it becomes a slightly easier for us to do these things. If there were other combinations, then we would have been in bigger trouble. So then we would have had to try out some algorithmic ways. But if the rules are simplistic like this, and if the string is also, can you give examples of, okay, so somebody has asked the question, if I can give same example of same concept to find probability of a sentence. So we do have that example after this, but that we will do using an algorithm. So here you can think this is like, so you have been asked to find the probability of the string AAAB. So the rules are anyway similar to how you would apply them had this been a, say, a sentence with four words. Say a is a word and b is a word, they do not represent letters but words, say, then it works in the exactly same way, and you can find it out using that. However, there are other methods to do that also, using algorithms and tables. So we will have a look at them just after this. This is a simplistic way, or if you have simple rules like this, and if you have, if the string is also straightforward, then you can apply things like this to get it done. All right. So yeah, basically that is that. So let's move on to the next part. All right. So this is going to take a bit of time and it can be a bit complicated. So we will go over this slowly. So somebody was asking if we have to find the probability of a given sentence. So here you have the grammar given over here. So there are 18 rules, and this grammar is in the CNF form. So the Chomsky normal form, it is already given in that. So you need to know this, that for applying the CKY algorithm, you have to first get the grammar into CNF form. Okay, so Chomsky normal form. If you like, that is the first step. Because the grammar over here has already been given in CNF, you don't need to worry about that. So we can directly apply the CKY algorithm. All right. So these are the rules. As you can see, there are 18 rules, and you have to find the probability. So you have to find the parse trees for the string "the boy likes the girl with a flower," and like, you can extend that question into thinking that if you get the parse trees, you can calculate their probabilities and you can sum them up to get the probability of the string. So what is important here is understanding what will be the parse trees. All right, and we will go over that. Okay, so we shall do this in the standard way. However, my representation will slightly be different from the representation that was given in the lecture. Effectively, we are doing the same thing, that is, we are working in a bottom up way. So what is bottom up? In the previous example, we did it in a top down fashion. So we started with the first rule, S gives AB or S gives BC, something like that. And then we are expanding the rules and we come down to the string. This is the other way round. We start with the string and we apply the rules in the reverse way, and we try to come up to the start symbol S. So this is the bottom up processing which is usually done in CKY algorithm, and this is what we will discuss over here. All right. So the first idea is that you first write down the string, each different word, they become a different column in this table. Okay. Now step 1, you look at the rules from where you get these terminals. So these words are the terminals, right? And there are some rules which yield terminals, and we know because of CNF there can be one non-terminal on the left hand side. So we have to look at how we get this. So for example, as you can see, most of the words like the only comes from det. Then boy comes from noun. Likes is interesting because likes comes from verb. Likes also comes from VP, and it also comes from CV. That is why we have to write down all the options. Okay, and then we do it for the rest of the string. So this step is straightforward. You just write down all the possible non-terminals that yield these terminals. This is the first step. All right. Now for the next step, what do we do over here? So the notation I am using over here is that so this is in this step we can combine all those things that are a distance of 1 apart from each other, or we can group two consecutive words or their non given respective non-terminals and see what rules can be used to reduce to that. So what do I mean without getting confused? So for example, if you look at this row over here, the leftmost column is marked cross. So there won't be an entry for this column. Why? Because we'll have to look at what we can combine the pairs to get. So if we pair up det and noun, whatever we get, that will be over here. We pair these two up and we write that over here. And we go on. So pairing these two up, we get that over here. So obviously we have 8 words, so there can be 7 possible pairs. So that is why the leftmost column is invalid, it won't have an entry. This indicates the combination of the first pair, which is the first and the second word. This is the second pair, which is second and third word, and so on. This is the seventh pair, which is the seventh and eighth word. All right. So now how do we do that? So you have a look at which rules combine any pair. So if we have a look at the rules, you see there is this rule like this, which is CN gives det noun. NP also gives det noun. And we have a like there are places where det noun occurs side by side. So we have det noun over here, we have det noun over here, and we have det noun over here, right? So we just combine them and we can either have NP or CN, NP or CN, NP or CN. So these are by combining pairs. So what you need to keep track of is which row you are on the table. So this is the second row. So we are looking at pairs. In the third row, we'll look at triplets and so on. And at the end, we'll be looking at the whole string together. That is how this works. All right. So, sorry. So we get this at the second row. Now we will be looking to combine triplets. That is, what are the possible combination from 3 things together. So when you do this, you need to keep track of what you are merging to get what. What do I mean by that? We'll have a look. So if you see, there is a rule like this, which is PP yields prep CN. So if we have a preposition and we have a CN after that, we can combine it using this rule PP. And we have over here prep and CN. So we can combine that and we get PP, right? Similarly, we also have the combination of VP, which gives verb NP. And there are possibilities of verb NP over here. How? There is a verb over here and there's an NP over here. So that is why we can combine them. Now, because at this row, we are looking at triplets. So for this word, we are looking at the past two words together with it. So that is why these two words have combined to give NP, and then verb and NP combined to give VP or CV. So you need to remember that these combinations VP and CV, they come from NP, not the CN part. Why do you need to remember that? Well, you can obviously have a look at the rules to see which things you combine to get what. But if you write it up in the table, it will be easier for you to do the parse tree. Here, due to lack of space, I could not do it. So that is why I am explaining slowly. So for example, over here, first we combine date and noun to get either NP or CN. Then we can combine verb and NP to get VP or CV. Similarly, over here, we combine date and noun to get NP or CN. And then we combine prep and CN to get PP. All right. So at this row, we are only looking at triplets. So we are looking at all those possible combinations of three words or three non-terminals together. Right. So we will go forward. Now what happened? Well, uh, then we can combine things over here. Right. So how are we combining them? So now we are looking at four words together. So we can look at these four together, and we have these combinations like CVPP gives VP. Cool. So because we have CVPP gives VP and we have CNPP gives NP. So CV and PP gives VP. CN and PP gives NP. What did I do over here? It's very important to understand this step. So when you are combining with this, right? So you are looking to combine this column with this column now. Now when you are looking to combine with this column, you can look at the very end or you can look above also. Because this is a combination with this part. In this, the verb part does not combine. But we can actually combine these rules, right? So this is what you need to take care of. And this will lead to the different parse trees. All right. So once more, over here, when we take CV with PP, then we get VP. But if we take CN with PP, we get NP. Now you need to remember, when we are combining CN with PP, then this verb part does not get into the parse. We need to take care of that. If we are combining CV with PP, CV has come by combining verb with NP. So that is not a problem. But CN did not come by combining the verb. So if we are combining CN with PP over here, the verb gets left out. We need to take care of that. So we will. Alright. But so far over here, we have got these two possible combinations. So once again, CV and PP gives VP, CN and PP gives NP. Alright. Rest of the things, we don't have any possible combinations. So we leave them out. At this level, again, we don't have anything to combine with. Why? Because in the previous step, we combined with this part. Now we have to combine with this part and we don't get anything yet. So we leave it as it is. Next row, we combine this and this. So the combination length keeps increasing as we go down the rows, right? So, and we have this combination of verb and NP together will give VP. Alright. If you look over here, verb and NP, sorry, yeah, verb and NP, that gives VP. So we get VP over here. Alright. So it's important to note that we already got VP, but that was through a different parse. This VP came by combining CV and PP. CV came by combining verb and NP. In this one, we are getting verb and NP, and this NP came by combining CN and PP. So that is why this is where the two parses separate out. So this is how we get multiple parses for the same string, because when we are combining, we can combine with the last value over here, or we can combine with values above them also. So if we combine with values above them, then we need to combine the rest of the part which was left out later. So that is all it's about. So here we get VP. Okay. And as you know, I did not write this, but there was another combination possible, which is CV, verb and NP. So this could well have been CV also, but as you will see in the next step, we won't get anything by taking it as CV. So we take it as VP itself. Finally, in this step, we combine this box with this box. So here we have an NP or a CN over here, and we use the main rule, which is S gives NP VP. So we have got VP on the right. We got it from two different parses, but we do have VP, and we have NP over here. So we combine them to get S. So this is our final objective, to get S. Now in the table which was constructed in the, or which was shown in the lectures, in that table this part is upside down, but essentially we are doing the exact same thing, because was some problem in representing it like that. I did like this, but effectively it means the same thing. First we are combining pairs, then triplets, then four things, then five things, so on, until the last step where we are combining the whole sentence. All right. So this is how we get this. So do you want me to walk through this part once more? Because after this we will just be creating the parts trees from this very table. So the most important step over here is understanding how we are constructing the table. All right, so we'll just walk over it once more. All right, first step. First step, we just write down the words as they are. Second step, we find out all those non-terminals which yield these words or terminals, and we get them over here. Most of them have come from a single non-terminal. Only this likes, it could have come from other combinations as well. Fine. In the next step, we try to combine pairs. So and the way I am writing is, if I combine column I and column I plus 1, the combination, then I'm writing in column I plus 1. So it's shifting to the right. At the end, as you are seeing that we are getting the values on the right hand side. So here date and noun combine to give NP or CN. Date and noun combine to give NP or CN. Date and noun combine to give NP or CN. There are no other possible combination of pairs in the form they are over here. So all rest of the things are empty. Only date and nouns could be combined at this step. Next step was we combine verb with NP, and the possible combinations are VP and CV. Similarly, over here we combine prep with CN and we get PP. So this is like triplets, three at a time. So we have previously considered date and noun together. Now we are considering prep along with that. Similarly, we had considered date and noun over here. Now we are considering the verb along with that. So if there was a rule which ended with verb, suppose there was a rule like CN verb gives something. So then that rule could have been applied over here, right? But we have to work with the rules that are given. So at every stage you look at where you are right now, what are the possible. So if you are looking at this cell, suppose we are over here, now you are looking at this cell. So you know whatever rule you will apply, that rule has to end with either NP or CN, right? So that is how you will look out for the rules. So you look in the rules, which rules end with NP or CN, and what do I have before that. So if you look over here, this rule ends with CN and this rule ends with NP. This also ends with NP. Now we need to see what do we have before that. So in this case, we have a preposition before that. That is why we combine prep and CN to get PP. Similarly, we have NP over here and we have verb before that. So we combine them to get VP or CV. So you have to write down all the possible combinations in every box that is there. Next step, we try to combine four things together like quadruplets. This is the interesting part for this problem, where we are looking to combine this row, the last row, with this row, right? So the simplest thing is we can do CV and PP, that gives VP. That is very straightforward. But you also need to look out whether we can combine PP with anything above this. Okay, and we can indeed, we can combine CN and PP to give NP. So that is why we have combined that one over here as well. So it's important to remember that this VP, it has come from CV and PP, and this CV has come from verb and NP. So that means this VP actually covers up till the verb, right? But the NP does not. NP has come from CN and PP, which means this NP part does not combine with the verb. The VP has already taken the verb into, like, we can, you can get the VP only by considering the verb along with it. But you, for the NP, you have to consider from det, not from verb. So for the NP part, this verb is still remaining. We have to think about that. In this step, nothing to combine with. And in this step, we can combine the verb and the NP. This VP is untouched because it has already combined with the verb. So we don't need to do anything for this. But for this one, this NP can combine with the verb to give VP. So we have two VPs. Like one VP is directly, like these are like, and like what I mean is that if you have a VP over here, there are different ways to break it down. That will lead to the different parts trees. So because we are building in the reverse order, bottom up, so that is why you need to keep a track of all the possible branches that come together to form the tree. Now it may very well have been that over here we wrote NP, but there is no rule like verb and NP, so we cannot combine NP. So then that gets lost and it's fine. Like not all possible combinations will be used in the tree, right? Like there was another combination over here, I forgot to write that one, which is probably we can combine verb and NP to get one more non-terminal. Yeah, so verb and NP gives CV as well, right? So we could have used that rule over here as well. So this would have been VP or CV, but then CV won't lead us to the final uh, string, so that's okay. But ideally CV should have been written here as well. I forgot to write that one. Okay, and finally in this step we have a VP over here and we have a NP over here. So we just directly combine NP and VP to give S. So if you know that in Chomsky normal form, there is only one rule which will have the start symbol on the LHS. So that is why you know that there is only one possible combination of non-terminals which will lead to the start terminal. And in our case, we knew that this is S gives NP VP. So we had to get VP at the end. So even though this could have been CV also, but it would not have led to anything. Alright. So this is how the final table looks like. Now the next step is you unravel through the table in the way you have combined them. So that is why I was mentioning. So suppose if you had written down over here, say VP, this VP came from verb and NP. So if you had written down over here in bracket verb and NP, so then you would have had an idea of which two were combined. But because of lack of space, I could not write that. So we'll just have a look at the rules once again to try to recollect which things we combined. So in this step, we have completed the table. Now we will go down in the reverse order and just write down the productions which leads to this string. How do we do that? So let's look. So this is now very similar to what we had done in the previous question, but this time we don't need to guess at what options we have. We can directly write down the productions from the table itself. All right. So the very first step, you know, S has come by combining NP and VP. So that is the first rule. Then we are taking this combination that this VP is created by verb and NP. So NP and this VP we extend into verb and NP. Then NP we are extending into CNPP. Then PP has been extended to prep CN. And then NP was broken down into det noun, CN was broken down into det noun, again CN broken down into det noun. So we now have this form, and then you know from here we directly go to the given string, the boy likes the girl with a flower. and you just apply the probability rules as you were doing in the previous questions. So this gives a probability of this. And the other possible tree, well, in this one we broke down the VP into verb and NP, right? What about this step where VP actually came by combining CV and PP? So this is the one we will explore now. So VP, we break it down into CV and PP. Now CV can be broken down into verb and NP. So we effectively get the same thing we got here, but we are following down a different parse. That is all. And thus we just expand, and as you keep on expanding it will keep getting easier because the combinations will reduce, and then finally we get this, and this is the probability. So the point of this question 3 is not about calculating the probabilities and the different parse trees, it's about this table, because it's about the CKY algorithm. So I hope you have understood the algorithm more or less. The idea about the algorithm is you need to keep a track of how many things you are combining at each step, and that is given by the row number. So first row we are just taking one combination, like the very word it came from. Second row we are combining two words. Third row we are combining triplets. Fourth row quadruplets, and so on. So that is the only thing you need to keep in mind, that at the given stage of the table, how many things are you combining? The second thing which you need to keep in mind is when you are combining with anything, say you are combining this column, the column starting with girl, with this column, the column starting with flower. So you can combine them at this stage where, like, because they are at a distance of 4 apart from each other, or 3 apart from each other. So when we are combining 4 of them, then we can look at combining them. So when we are looking at combining them, you have to look at the possible combinations, like both at this level and any level above it. Okay, so that is why CV and PP gave VP and CN and PP gave NP. So both these rules got reduced over here, but they are coming from two different levels. And then you need to keep a track that since you have used the combination of CN, since you have used the combination with CN, that means you have left out the verb, and that verb needs to be combined at the end. Otherwise, this parse won't work. So because luckily we had that rule of verb and NP gives VP, so we could reduce this NP to VP again, and thus it was okay. Otherwise, if we would not have been able to reduce, then this would have been the only valid parse. Alright. So it's all about this table. When you combine, carefully look at the possible rows, possible columns you are combining, and what are the possible non-terminals at each stage of that column. So if you can combine with something which is higher up in the column, that is also you need to take that into account, especially if you have been asked to find out all possible parse trees. If you have been asked that just give one parse tree for a given string, then it's fine, you don't need to look at all combinations, you just need to get one working combination that leads you down to the start symbol. But if you have to look at all possible parse trees, and it's a good practice anyway, because you might not always know which combinations will lead you to S. So you look at all possible combinations at every step. And that is why over here, we combine CV with PP to get VP. We also combine CN with PP to get NP. Alright. And the rest of the things are straightforward. Okay, I guess this is clear then. It is all about creating that table. The rest of the things are very similar to how you would do these problems. So that is basically you write down the rules, keep multiplying the probabilities, and that will give you the parse tree. Alright. So to end today's session, we have, like, after these big questions, we have some light-hearted questions. So we have two true and false questions. The first one is, it requires 2n minus 1 distinct production rules in CNF to generate a string W of length n. So given that the grammar is in Chomsky normal form, to generate a string of length n, how many production rules will have to be applied? So the question says it's 2n minus 1 distinct production rules. So could anybody say whether this is true or false? Like, have a guess. Well, all right. Uh, let's look at the process. So somebody said false, and that is right. So this is not correct. So why we'll explain. So in CNF, we start with the start terminal S, which has length 1. After that, we can use n minus 1 production rules in the form non-terminal gives non-terminal non-terminal. And that will give us a string of n non-terminals. And then we can apply n rules of the form non-terminal gives terminal to get a string of n terminals. So this is how we can generate a string of length n from the start symbol S for any grammar. But the key thing is we have applied a total of 2n minus 1 rules. So you need 2n minus 1 rules at least. But all these rules may not be distinct. So in the question it has been mentioned distinct. They may not be distinct rules. So that is why this is false. And the second one, this is like a simple question on the inside out probability questions. So because that is a bit complex, so we have not covered to solve them. This is just the theoretical portion. So this says that probability of the word that starts from 1 to m, given this non-terminal n, which generates anything between length p and length q. Okay, so that is given by this. That is the product of the inside and outside probabilities of P and Q over all J. So this is the statement. So I'll go directly into the solution. So as we know, this is the formula for inside outside probability multiplication. So if we have let's consider any one particular non-terminal nj which spans from P to Q. All right, so then this looks like this, where we first do probability of word from 1 to p minus 1 and from q plus 1 to m, and in between, that is p to q, we take nj into probability of generating the word which is p to q from this nj, and that is basically alpha j and beta j. So what are these J's? J's are the possibility of all non-terminals which can be placed in this position between P and Q, or which non-terminal leads to the string WPQ. So if we just sum over all the J's, then we get this. So like probability of NPQ is like we have to look at the all individual probabilities of all non-terminals which can reduce between P and Q. So we just sum over all j, and that gives this statement which was given in that question. So this is true. All right. So here I have come to the end of today's session. So if you have any doubt, you can ask regarding the questions we have discussed. All right. I guess there are not many doubts for today. So, all right. Um, we can end today's session then. So, thank you everyone, and we shall meet next week. Okay.